So really these cancel out. We don't need them, okay? And then this really is the only important part of the expression. This is the antiderivative to this expression here. Now there's no plus c. We're going to put limits on this integral. Well, let's look at the distance that x can be. The lowest distance x can be is 0. Okay, let's put that there, 0. Let's do our evaluation thing over here. So from 0 is the lower limit. The upper limit, the maximum is L. Okay, the rod is only length L. Let me make this a little cleaner. I'll rewrite it, and then we'll switch to, I think, a second sheet of paper to talk about our evaluation and our verification of the expression here. E equals K lambda I hat times the expression R plus L over 2 minus X to the negative 1 power. Remember that negative 1 power, you know, actually I changed my mind. I'm just going to rewrite this as the fraction. Remember it's a negative 1 power, which means it's in the denominator. So let's just go ahead and do that. R plus L over 2 minus X. We don't need the expression, the exponent anymore. And that's evaluated between 0 and L. Okay, so this is our formula. Keep in mind we don't know what charge density is, but that's, you know, they give us the charge and the length here. We can just figure that out real quick. Let's see, Q over L, which equals 3 times 10 to the negative 9 coulombs over 0.05 meters. Lambda ends up being, what I have over here in my previous, 6, right? Yeah, 6 times 10 to the negative 8th. Keep track of our units, that's coulombs per meter. Okay. Anyways, I'm going to call this our expression, so check, that's solved. Let's talk about verifying that this expression has expected behavior. We can ignore all these fancy constants out here, those are just whatever. Let's look at this denominator here. So let's say R is, the maximum you could have for R here is, excuse me, the minimum you could have for R here is L over 2, right? That would just be kind of touching in the same space as the particle at the very, very end of this rod. So let's say you have that, you know, 1 over L over 2 plus L over 2. Okay, so that's our minimum R minus X. Well, let's see. In evaluating this expression, we're going to have our maximum value of X be L. So what happens when you have L over 2 plus L over 2 minus L? You end up with 1 over 0. Psh, the world explodes. Okay. That would mean that basically if this superposition was in the same space as the particle on the end of our rod, the electric field strength would go to infinity. Alright, so that behavior makes sense. Other than, you know, if the distance here is anything large, this fraction is going to be some, let's say it's going to be 1 over some big number. Okay, because X still has its limits within 0 and L here. So let's say this number is like just a big number, okay, minus L. It's going to end up making the fraction approaching 0. So it's going to be a very small number, which makes sense. You know, the farther away you are from your rod, the electric field strength is going to go down. Alright, so let's go ahead and do an evaluation. Let me throw up a second sheet of paper here. Copy down our formula first real quick. Makes it easier for me. And times 1 over R plus L over 2 minus x, evaluated between 0 and L. Alright, so let me copy down our constants. Okay, so for our evaluation, R equals 0.03 meters, L equals 0.05 meters, and Q equals 3 times 10 to the negative 9 coulombs. And I already calculated charge density, so I'll just put that down here. That's 6 times 10 to the negative 8th coulombs per meter. Okay, let me bring it all. I think that's everything I need, yeah? Okay, let me bring it all up here. There, that's what I was writing down while you guys are going, what the heck is he doing? Mark where the bottom of the page is. Okay, let's start plugging and chugging. That's all you have to do at this point. Let's see, K is, I'll just write it all out so we can keep track of units, and then I'm just going to tell you the number I came up with on my calculator. So 9 times 10 to the 9th, and remember our constant is newtons meters squared over coulombs squared. That's just the way I write it. Times our charge density, which is 6 times 10 to the negative 8th coulombs per meter, times I hat, just put that in there. Okay, so we know that it goes in the x direction. Times the quantity of this thing we got to evaluate here. So let's start with the first part. With our maximum value is L, so R is 0.03 meters plus L over 2. I'm just going to write this down up top here. So R plus L over 2 equals 0.055 meters. Okay, so we're going to say 0.055 meters minus 0.05 meters. Okay, and then it's going to kind of go into this area over here. 1 minus our minimum value, okay, where x is 0, would just be R plus L over 2 in the denominator, so that's just 1 over 0.055 meters. Okay, alright, let's make sure all of our units are right, and make sure I didn't forget anything here. We have 1 coulomb here, that cancels out that square there. We've got meters times this is going to end up being 1 over meters, so that's 2 meters in the denominator. Bam, that goes away there. That takes away takes away the m squared, and you end up with just a value in the units newtons per coulomb, which is good because that's what we want for our electric field strength. Anyway, so when I crunched this all on my calculator, I ended up with 98182 newtons per coulomb. Let's keep respect to our significant figures, which they only gave us 2 digits, so we should actually really write this as let's just do 9.8 times 10 to the 4th newtons per coulomb. Okay, so there's our answer to the part where it had us evaluate it. This is our expression right here, and the behavior seems to make sense. Alright, hope that answered everybody's questions.